please.
Yes, sir.
Let me start. Okay, so thank you very much for inviting me here. I'm Daisuke Bekki from Semantics University that is located in Tokyo. It's one of the universities in Tokyo. And today's talk is about proof-theoretic investigation of natural language semantics. This is in a way that, well, not mathematical or computational linguistics or proofs. It is more about proofs for mathematical and computational linguistics, but it's not a big difference, I hope. So this is about the semantic framework, which we call dependent type semantics, in short, DS. We've been working on this for a past decade, and it's basically a framework for natural language semantics. And especially, it is a unified approach to general inferences on one hand, and an upfront supposition resolution in terms of type checking and proof construction on the other hand. So what is an upfront solution? I will talk about a bit about later. Basically, it has four features. The first one is that, clicking the wrong button. So it's a proof-theoretic semantics. So it is not based on the notions such as denotations and models as the standard model theory does, but rather on proof-theoretic concept as proof and context. And secondly, it's about a theory about anaphora and presupposition. So if you're a linguist, you might understand it as a proof-theoretic alternative to dynamic semantics. Thirdly, it is positional theory. So if you are a syntactician, maybe if you're a syntactician, you may use it as your semantic interface. And fourthly, it has implementation. So we have implemented the theory by Uphill programming language. So you may find the code in the GitHub repository. So in a sense, it has some connection to natural language processing, although it doesn't make use of LLM behind. So okay, so let me start from the dependent types. Maybe some of you are familiar with the notion better than me, but let me do this in order to confirm what I'm doing. Okay, so this is the godfather of the dependent type theory of Martin Leff. So theory had started from this type theory. But the idea of investigating natural language semantics based on this type theory has been done by these legendary people, including here. And so, so the dependent type theory basically adapts the two very important dependent types. So the one is the pi types, and the other is called the sigma type. And pi type is basically, well, but this is a simple function space, whereas this is a space for pi type. So basically, in a simple function space, the codomain is a single domain, whereas in a dependent or the fiber function space, codomain might be divided into the families of codomains, and they have indices, and this comes from the element in the domain. So this is fiber, and the sigma type is a similar idea, but it is about the pairs. So this is a simple product space, so in which the second domain is a singular domain. On the other hand, in the sigma types or the fiber product space, the second domain is family domains, and which they have also indices, which comes from the first element pair. So this is also fiber. And we use a slightly different notation deviated from the standard notation like this. And our notation is like this. So we put emphasis on the status of these things. These are basically extension of function type and the product type. And we have to be careful about the fact that pi type is a generalization of implication and universal quantification. When this X doesn't appear free in B, then it reduces to implication, and that if it's not, then it can be regarded as a universal quantification. The difference is that whether B is a family of domains or a single domain. And same thing can be said to sigma type. So this is extension of a product type, but it's a unified notion of a conjunction and existential quantification. If this X appears free in B, then it reduces to a conjunction. But if it's not, then it plays a role of existential quantification. And we also adapt this special notation. Basically, they are the notational variants. They are the same thing. And we call this vertical notation. And it is convenient to write a very huge semantic representation for natural language. And also, we have to note that the scope of this X is this pink rectangle, whereas this scope of this blue X and the sigma type is this blue rectangle. So this plays a role when we talked about the quantifications and the number. Okay. And the behavior of dependent types, at least for sigma types, is captured by the set of these rules, which consist of formation rule and introduction rule and elimination rule, as you know. So the formation rule basically says what is the conditions for this guy to be a well-formed structure. And so the idea is that the set of formation rules for all types defines what can be counted as types. And in the introduction rule, the pi type appears here on the right-hand side of the last line. So it shows how this type, which is also regarded as a position, can be proven. Okay, so this is also regarded as a lambda introduction rule, and this is elimination rule, the pi type. So basically, the pi type appears here on the left-hand side of the upper level. So it's basically shows how we can use the proof of this type. So if we have this, and this is a proof of this pi type, then additionally, if we have this, then we can use this to conclude that we can have the proof of some of these. Okay, and one thing I want to emphasize here is that proof of pi type is a function. So that plays a role when we talk about linguistic stuff, like here. And so these are the set of rules which governs the behavior of sigma types. Again, these are defined in terms of tripod of rules, formation rule, introduction rule, and the elimination rules. So the introduction rules, the formation rule says the condition under which this is the type. And the introduction rule shows how we can show this proposition. So basically, the proof of the sigma type is a pair of M and N, where M is of type A and N is of type G, that which index is instantiated by this guy. And the elimination rule is about how to use the proof of the sigma type. So these are the projections. So because this is some kind of a pair, we can take the first projection to get the proof of A, and we can take the second projection to get the sum of B's. Okay. And there is additional notations. So if this sigma type reduces to a conjunction, then we can also use this vertical version of conjunction notation. And if this pi type is reducible to implication, then we can just use notation A to B just as simple types. And negation is, as always, defined as a function from A to uncertainty. Okay, so here's some example, natural language example. So the semantic representation of every student is told is like 1B, where we use pi type because every introduces a universal quantification. So this uses a pi type. But in the domain of the pi type, here is sigma type embedded in the pi type. So this sigma type is a pair of entity type and the student of X type. So this is a dependence type. So technically speaking, this entity type is defined as an enumeration type in Martin-Lew's type theory. But I don't want to get into the details here. But basically, this is a finite sequence of entities. And student of X is a complex type, and that is a collection of proof showing that X is a student. So, and as a whole, this function, function belonging to this type sends the pair of entity and the proof of its being a student to a proof of the tallness of the first guy. So that is the entity in questions. So then the truth condition of this sentence is in DTS, it is regarded as inhabitants of this type. It means that when there is a function of this type, it means that we can send any kind of student entity to its tallness. So when that kind of function exists, it means that every student is tall. Okay? So the truth condition is a proof inheritance in this area. And the second example is some student is tall. Some semantic representation is almost the same as 1B, but as a whole, it is a sigma type. So it is a nesting of the sigma types. So the first element is this U of the type. U is a kind of pair of the entity and the proof of its being student. And it is paired with the proof of the tallness of this guy. So the truth condition again in 2A is that if there exists the kind of the tree structures consisting of the pairs, or in other words, if there is a triple of entity and student X and the tool by 1U, then we can say that that guy is a student and a tool. So it is sufficient to say that some student is told. Okay. The third example, no student is told. We can just put the negation sign on top of the sigma type. So this is basically, it is not the case that some student is told. Okay. So, but if we recall that this negation is defined as a special case of the pi type, so it sends this triple to the uncertainty. So it means that if there is a student who is told, then it leads to contradiction. So that is the meaning of this semantic representation. Okay. Okay. So and we have talked about pi type and sigma type, and also a bit about the enumeration type. In the full-fledged version of DTS, employs almost all the types which Martin-Lev type theory introduced. Like intentional equality type for the equalities, disjoint union type for the disjunctions, enumeration type for the definition of entities and certainty and truth. Natural number is also necessary, and we sometimes use type universe. But the point is that in DTS, we expand the Martin-Lev type theory with one kind of new type, which is called underspecified type. So that is the whole point of DTS. We use this for subvolution triggers when linguistically speaking, but it is logically speaking, it corresponds to open proofs maybe. And so we're going to talk about how we use the specified type to analyze anaphora in natural language. But before doing that, let me briefly talk about what was a puzzle in anaphora in natural language. In case you don't know it, okay. Yeah, but okay, just briefly. So the theory of anaphora starts in the 1960s or 1970s in the past, and basically it started from the use of the pronouns, and it was classified in two ways. One is a deictic use, and one is an anaphoric use, and there are differences in the use. For example, the deictic use is like this. So if I point to John over there, and I say he was born in Detroit. So in that utterance, he means just John. So in a logic textbook, it can be described as by just using the names. So this is an example where we don't need a special logic to describe the meaning. So deictic use can be described by just using the name. And the second example is one of the anaphoric use for reference. John loves a girl who hates him. This him can be ambiguous. So regarding with respect to his antecedent, but one of its reading is just referring to John. So in this case, the semantic representation is just this can be described just using the name J. So in this sense, these two are doesn't need a special logic. Then the third example is a bound variable anaphora. Every boy loves his father, and again, his father has many meanings. But one of it is as every boy loves his own father. So in that case, we need to use the bound variable like X here. So this is where the name bound variable anaphora comes from. We use the bound variable of the logic here. But anyway, these three examples is not the cases where we need to extend semantic or the logical language. But in the case of so-called E-type anaphora and the donkey anaphora, there had been a puzzle for long years, and for example, E-type anaphora, a man entered into the park, he was sold. So this he can refer to this is not a man who we don't know exactly, but someone was introduced and this was first sentence. And in the case of donkey anaphora, every farmer who owns a donkey pays it. So it can refer to a donkey here. If a farmer owns a donkey, he pays it. This is another version, but it can refer to a donkey here again. So there is a certain challenge which I call the tension between the dynamics and compositionality, which I will briefly explain in the next slide. There are other more complicated cases as well. Anaphora not representable by first-order logic nor dynamic semantics. So, for example, 10, every girl received a present. Some girls opened it. So this it can refer to a present which is given to this girl. Okay. So this is the case. DTS can deal with this case as well, but it is not included in this talk today. But and another example is killer example. So the disjunctive antecedent. If Mary sees a horse or pony, she waves to it. This is written in the textbook. So the antecedent of it is a horse or pony. We don't know which, but anyway, we can refer to horse or pony, whichever Mary sees. Okay?
I never heard a name, syllogistic anaphora. Where does that come from?
Oh, this is well, we named it.
The example I learned from Lauri Karpponen.
Okay, thank you very much.
Early 70s.
Early 70s, okay. So the programmatic aspect of the donkey sentence, well, this is classical argument. So I want to go over it just quickly, but basically, conditionally, these sentences is, at least in one of the readings is equivalent to 13. So for every farmer, for every donkey which is owned by X, then X, Y in the beating relation. But the problem is that the A donkey indefinite noun phrase is translated into the universal quantification. This is not well, because if we allow this, then John has a donkey may mean John has every donkey. That is weird, right? So we'd like to we want to stick to the translation that indefinite is translated into existential quantification. But if we do that, then we obtain the semantic representation like 14, but this Y gets unbound. So unbound variable gives us a different truth condition than 12A and 12B. So here is a tension between the translation. Well, that is about the compositionality on one hand, and the truth condition meaning, especially its dynamic meaning on the other hand. So this has launched so many dynamic semantics in 80s, starting from the DLT, and well, they are still upgrading by using a complex version of the dynamic logic. But on the other hand, we have the different disciplines starting from the Sandholm in 1986, and this is called the type theoretical semantics or the type theoretical discipline. And my work is on this, following this line of researches. And so, what is a good point of type theoretical approaches? So here's the argument. So this is a donkey sentence, the computational version. And this is a slightly adapted version of semantic representation by using sigma type and pi types. So the point is that, well, this is a universal quantification. So as a whole, it is a pi type. So it's a function from this guy into this guy. But this is a nesting of the sigma types because basically a relative pronoun introduces the conjunction. And here is a indefinite, so it is translated into the existential quantification that is represented by the sigma type. So it's a nesting of the sigma type. So this U is a kind of a printable, right, English? Printable. So it consists of a certain entity that it has a proof of being a farmer. And there is another entity Y, which has a proof of being a donkey. And the fifth one is owning a proof of owning relation between this guy and this guy. So this is a printable. And when there exists a function of this type, it can send any of this type of printable into a beating relation proof, where pi1 u is this guy, and pi1 factor u is this guy. So it's a beating relation between the first and third. So this briefly represents the truth condition of the especially strong reading of 12. But the point here, or the magic tricks here is that, well, this is the existential quantification introduced by a donkey, whose scope is this pink rectangle. So in that sense, the semantic representation of it here is still outside the scope of this existential quantification. However, this stays within the scope of U because it's within the this blue rectangle. So it can make use of this U, which is a quintable, and we can put together projection functions in this way. Then we can disintegrate the proof of U and pick up the first guy and pick up the third guy. So in the end, we can talk about the internal structure of this U. So this is, although this state of type scope of Y, still it can refer to that Y. So that is a magic trick when we introduce the dependence type to describe the meaning of 12A. So, this was my starting point. So there is questions if we want to extend this idea to a full-fledged linguistic theory or full-fledged semantic theory. So the question is, how could one get to these nicely dependently typed representation from arbitrary sentence, rather than just saying that this is a representation of this sentence? Okay, so the standard answer by linguists would be like by lexicalization. So we're gonna lexicalize the meaning of the sentences and combine it by along the line of syntactic structures. But the second question is, how could we lexicalize context-dependent words like pronouns? So like this. So if this is a semantic representation of it or he or some sort of things, where this U comes from. So this U is this U, which is introduced by the universal quantification that belongs to the different lexical entries than the pronoun itself. So how can the pronoun know that we can refer to you in this context? So here is our answer from DTS. So we do this by using underspecified types, and how we can retrieve a context for an underspecified type. We use type checking, and how can a pronoun find its antecedent? We use proof constructions. So this is the basic architecture of DTS. And so the point is the introduction of this underspecified type. The logical language we use in DTS is called UDTT. So that stands for underspecified dependent type theory, which is defined as DTT plus underspecified type. So this is the notation for underspecified type, which looks very similar to sigma types. It's intentional, but it's basically a different thing. The intuition of this type is that basically it is B. Basically, it is a type B, but it may make use of X, which is a proof of A. That is presupposed. So A is presupposed to be true, although we don't know the exact proof of it. So that is the intuition of underspecified type. That in order for this guy to be a well-formed type, we need three conditions to hold. The first one is that A itself must be a well-formed type. And the second one is that this A must inhabit the proof. So in other words, it must be true. It must be actually true. And after that, we substitute the occurrence of X and B with what is found and check if it is a well-formed type. Then if all these three conditions meet, then we can say that this is a well-formed type. But the point is that if we execute the type check for the preterm that contains occurrence of underspecified type, then that type check will launch proof search and this step. So the proof search between or during the type check. So that is point formulation. Okay, and this is organization of the grammar or the meaning theory. So if we have the sentences and we adapt some kind of syntactic theory, which we call star CCG. I don't have a time to talk about this version of CCG today, but this is my thing. And but anyway, So this yields semantic representation in UDTT, and we put all things together and get discourse representations. And when we conduct a type checking, as I just said, if it contains enough presupposition, it means that there are underspecified types in the preterm, so it launches some proof search. But as a result of the type checking, we have not only a preterm but proof diagram of the well-formed network semantic representation in UDTT, and this is a representation, semantic representation where the antecedent of anaphora is absorbed in some way or another. And there is a proof transformation called aspirant elimination. It basically removes every occurrence of the underspecified type contained in this proof diagram, and ends up in the proof diagram of described in dependent type theory, which have no underspecification. So in the end, we have the types and DTT. So we can conduct some inferences here. So this is the organization. So this is a lexicon in the CCG, but no, I don't get into the details of these things, but let me just say that these are quite standard. If we agree that every and if conditional is represented by using by type, and conjunction like relative nouns and so things are represented by using sigma type, and pronouns and presupposition triggers are represented by underspecified types. So these aspirants are the specification. And this is the syntactic structure. And this is just a standard syntactic structure, and we conduct semantic composition along the rules specified in the syntactic structure. And we can just do this mechanically. And this is a representation of farmer on the donkey. So this is not a proof diagram. So this is just a record of the calculation of the semantic compositions. And every farmer who the donkey beats it, then we have this semantic representation, and this pink rectangle shows something underspecified in this sentence. So basically, it presupposes the existence of some non-human. So that is that must be the antecedent of it. Okay, and we want to find it from somewhere around here. Okay. So this is the semantic proposition, and then we conduct type checking for what we obtain. So type checking of this calls for pi formation rule first. This must be well-formed type, and this must be a well-formed type as well. However, in the proof of the latter, we can make use of the assumption that this is true. Oh, it's okay. This argument comes from the definition of the formation rule of the pi type and sigma type. So then this is the specified type, and here are three conditions. And the first one is this itself must be a type. And second one is we have to find proof of this from these assumptions. So intuitively speaking, we assume the existence of the farmer who owns a donkey, and we try to construct some non-human from it. Okay, and maybe this donkey. And this is can be formally done in this way if we make use of some working knowledge that every donkey is non-human. So we can draw this proof diagram, and this is a proof diagram of the distance for the non-human from the distance of the farmer for the donkey. and we take the first projection of it, then this is a donkey expression, and resulting semantic representation obtained by replacing the unspecified type with what is found. Okay, so here's the takeaway. The semantic representation of the pronoun can refer to a donkey in question even from the outside of its existence. Because the donkey in question can be constructed from the variable such. So in short, anaphora applicability is deducibility. So this is a claim that TTS makes. And here are some notes for linguists, maybe. The same analysis applies to the implicational version of donkey sentence as in 15. And but I avoided to use this sentence because it has two pronouns, so it needs a bigger proof diagram. So it's not for introduction. And the second note is that this analysis only predicts so-called strong reading for the donkey sentence. For driving strong and weak readings, so we need to refine the definition of the quantifiers, and we have discussed this issue in Tanaka 2021. And the third note is that if we refine the analysis as described in Tanaka, then we can also explain the algebraic link like in 16, which is known as a parameterized sum individual in PRIFPA 1996. So this is a bit complex case. Every farmer owns a donkey and loves its tail. So this is just a donkey and a frog. But in the second sentence, they beat it. So they beat it means that each of them is a farmer and beat the donkey he or she owns. So there is a dependency between they and it in the second sentence, which comes from the dependency in the first sentence. By using pi types, that dependency is coded in the type, so we can just copy the relations without saying anything about it. Okay, so how many minutes do I have? So, like 20 minutes. So, okay, thank you. So, so far, we briefly talked about introduction about the yes and what it is about. But some of the audience have participated in my talk somewhere, and I have talked about them in various places. So I think I need some new material for the people who have familiar with my arguments. So here is some stuff which I haven't written on the any page yet. So this is a discussion on anaphoric potential. So what is anaphoric potential? So this comes from the arguments in the dynamic semantics discipline. So one of the central insights of dynamic semantics is that the meaning of a sentence is not exhausted by its truth condition alone. Rather, there is a certain kind of information which is called anaphoric potential, which differentiates the 70A and 70B, even though these are, at least in the classical logic, equivalent proof-theoretically and semantically. Okay. Well, 70A is some company is not rich, and 70B is it is not the case that every company is rich. Okay, so in the standard logic textbook, they could be translated as formulae and script 18A and B. Some company is not rich, and it is not the case that every company is rich. Okay. So, however, if we investigates the certain kind of continuation for these sentences, like 90B and 20B. There is a crucial difference between the 90A and 20A. For example, some company is not rich. It can be continued as it doesn't have enough money to replace the systems, and it here can refer to some company. So this is okay. However, it is not the case that every company is rich. Then it is asserted to continue as it doesn't have enough money to replace the system. So this pronoun has a difficulty in finding it antecedent from something provided by every company. Okay, so the inability of sentence 17B, that is 20A, and to provide antecedent for the pronoun from A highlights that while it is truth conditionally equivalent, these are truth conditionally equivalent, and that it fails to introduce the difficult referent that can be subsequently accessed. So there are certain differences, and it is called anaphoric potential, and it is maybe important to explain what kind of information they are. So if those semantic information, the anaphoric potential is a fundamental component of its meaning. Okay, so that motivated dynamic semantics to move beyond the purely truth conditional approach toward something called context change potential. That interestingly, dependent types gives this issue quite different solution. So the semantic representation of the meaning discourses, which I have presented just 1 minute ago, is like 21A and 21B. So this is a representation for some company is not rich, and this is well, these are conjoined, and this is it doesn't have one. Okay? And this is it is not the case that it is rich, and it doesn't have money. Okay. In the first case, the antecedent for the subsequent anaphoric pronoun can be successfully resolved as in the first projection of this F, because this is a sigma nesting of the sigma type. Basically, it's kind of triple. We can pick up any guys by just using the projection. So this has the power to provide a antecedent subsequent discourse. On the other hand, it is not straightforward if the first sentence is this representation, because this is basically a nesting of the functions. The negation is a function sending this guy to absurdity, but this guy is also a function type, so it is a function sending entity, company entity to richness, but it is not straightforward to pick up one particular company from this representations. So basically, the different representation in DTS for 21A and 21B gives a straightforward explanation of why the first one provides antecedent and the second one provides doesn't provide antecedent. But here we need to be careful about one aspect, that this explanatory power of DTS comes from the status as an intuitionistic type theory. The situation can be different if we add classical rules to DTS, such as double negation elimination, formulated in this way, for example. And the point is that if this inference has a proof, then an anaphoric thinking question would be wrongly predicted to be licensed. So this is schema for the semantic representation, so it is not the case that every company is rich. And if it deduces the proof of the existence and some company which is not rich, then we can convert the second sentence into the semantic representation of the first sentence, from which we can pick up an antecedent, right? And actually, this is doable in this way. So if we can make use of DNA like this, so this is a first representation of the first sentence. No, this is the negation of this is representation of the first sentence, and we make use of DNA twice and have the representation for the second sentence. So it means that apart from the details, this means that adding DNA makes DTS a system of classical logic, thereby causing to lose its ability to distinguish the different anaphoric potentials. So the explainability of DGS on this anaphoric potential issue is depending on the its status of being intuitionistic logic. So, but interesting thing here is that the explanation of anaphoric potentials, especially the difference between the two sentences, comes from the strength of the proof system. So although this is kind of a controversial conclusion that we have to say that natural language inferences and also inferences which we make to find the pronoun antecedent must be intuitionistic. But I think this is one of the proof-theoretic trial to give some explanation to some certain linguistic puzzles. Okay, so here's a summary. I hope there are questions to fill the 10 minutes. So as a summary, DTS provides a unified analysis for general inferences and for resolution mechanism. So, and the background theory of DTS is what we call UDTT. So it's an extension of DTT with the specified types. The point these, so lexical items for anaphoric expressions and presupposition triggers are represented by using underspecified types. And the context retrieval for these underspecified type reduces to type checking. So this is analyzed in a completely type theoretical manner. And anaphoric resolution and also presupposition binding, which I haven't discussed in this talk in DTS, reduces to proof search. So in other words, anaphoric accessibility reduces to proof constructability. And there is a proof transformation from UDTT to DTT. There is a total function that basically transforms the proof diagram of UDTT into that of DTT, by which semantic representation and DTT is obtained with all anaphora presupposition result. So this is my design of theory of semantics, and here's some history. Okay, starting from Sandholm 86, it's a handbook of logic and handbook article introducing the pi types and sigma types, and briefly mentions its possibility to applying it to a donkey anaphora, but it started it. Okay, and some of the early works and TTG, and there are some works that among them Kramel and Piwek's work introduces the idea of anaphora resolution as a proof construction. So my work is based on that idea. Although their work is placed in the context where all the inferences are done in prologue, and they didn't talk about the functionality, but the intuition comes from their work. Okay. And that is first generation, and the second generation starts from the Robin Cooper's TTR and Zoe Liu's MTT semantics, a series of works. And there is also works by Daisuke and Zablowski. And this is where my work has started. So based on the DS framework, we have analyzed different kind of linguistic phenomena, including generalized point-by amplification, and also extension to conventional implicature and to 6. Okay. Okay, we have also investigated some of the implementations and also some integration of this whole grammar or the theory of semantics, theory of meaning with a deep neural network to get some funding. This is not, what is necessary in this work, but a hybrid approach is also interesting, especially, for example, if we obtain knowledge like every farmer is a non-human out of blue, then sometimes neural networks can help us providing that kind of knowledge from nowhere. Okay. Okay. Thank you very much. So I think this whole presentation makes sense.
Are there any questions? Yes.
How good is DTS at predicting like, do you have any instance where DTS predicts that you wouldn't be able to refer to something, but you can, or vice versa?
Yeah. So I can answer it in 2 or 3 ways. Firstly, there is if you are familiar with discipline of dynamic semantics, many empirical fact has been accumulated, and this anaphora is okay, this anaphora is out, and basically we can do what they can do. Okay. Okay. And secondly, we have some additional materials which I skipped, like logistic anaphora and disjunctive anaphora. They are some of the examples that differentiate approaches to dynamic semantics. So I think we can do much more than the dynamic semantics. Okay, thank you.
More questions? Yeah, it's great to see these developments, especially the last slide, which you didn't show in more detail. I would like to add one thing to the history, and that is Hinteka's game theoretical semantics, which had in the 70s already a very, I think, a very good explanation of the donkey sentences and also the syllogistic anaphora.
Yeah.
And it was also very important for me because I then, starting with, I found that the game semantics corresponds very well to type theoretical, this is sigma and pi types, and so that led to kind of a formalization of Hinteka's game semantics, which then became the background. But and I think it was not very well noticed by any linguist at the time, which was a pity. These game semantics. So if you have looked at it, so you know the point. But the other thing that I was just wondering, these underspecified types. So at the time, and which you are certainly aware of, so in the I used identity functions for the anaphoric expressions. So for instance, a Bron is a function which takes a type and an element of that type as its arguments. And then if you are, and in the linearization, it produces a pronoun which whose gender may depend on the type. And the same thing for the definite phrase. So it takes a type and then it produces in linearization the phrase the a or the man or the dog or something. But then it has this argument for the individual. And when you are parsing something, you are give a type theoretical term which has a question mark, a meta variable for, if it is a pronoun, you have a meta variable for the type and the individual, but for the definite descriptions only for the individual. And then you have to do the proof search, which is open or quite straightforward because exactly the same way as in your case. But so I'm not quite sure if this is just a notational variant of the underspecified types or if it is underspecified types are somehow more general than these identity functions.
I have memory that I have investigated the difference between your formulation and the specified type and 10 years ago, but what I vaguely remember is that when we want to compose, for example, the presupposition trigger, the different article with its contents, and there was some variable flash, and once we regard the specification just an ordinary variable, so we have to give some meta status for the specification, and that was the motivation, if I remember correctly.
We can discuss it.
Yeah.
This was very fascinating.
Okay. Ask the question.
So
close this one.
yeah, that's what we did. Where do we find the?
So there's problem.
Yes, we did that.